I'll think about that for next year. All right, so calendar, we are now here where challenge 3 is due. Today, turns out we made pretty good time on graphs. What I thought had been divided into 3 had only been divided into 2, so we are a little bit ahead. So today we are going to talk about minimum spanning trees because we made it all the way through graphs. And then next week we will talk a little bit more about minimum spanning trees and probably start shortest path on Monday and then continue with it because it's kind of a bigger topic. So programming challenge 3 is due today. So most people done that already or signed up at least? Yeah, signed up? Okay. All right. So last time we were talking about graphs, and if you remember, the graph is this thing where we have these vertices, these edges, they're connected. We generally only want to talk about the kind that have no loops back to themselves and are considered a simple graph. So they look kind of like this. Sometimes we'll have directed edges, sometimes undirected edges. Last time we talked about this idea of depth first search, and that's if we want to start at one node and maybe we're looking to get to another node, or maybe we just want to explore the entire graph, or maybe we're looking for a node that's not there. This was one way that we could go about traversing this data structure. And the idea here was that we would kind of go as far as we could with our node's first neighbor before we came back and tried the second neighbor. So here's our example that we ran through and how we traversed that. And so this, we talked about, is a way to find a path in the graph from one node to another, if there is a path. But it may not be the shortest path. It will just provide a path. Then we compared that to breadth first search, which rather than going as far as we can with one neighbor, kind of does a neighbor at a time and goes a layer at a time and works its way out. It had a major benefit of it will always find the shortest path, right, whenever we go through our graph. So if there is a path there, it will be the shortest path that's returned. And remember that when we're talking about shortest path here, we're talking just about the number of edges that we have to traverse. So no weights on the edges or anything like that. And if you think about this in terms of like real applications, typically edges will have some kind of cost associated with them that may not be, it may not correspond one-to-one with the number of edges. So you may be optimizing on something that's not just the number of edges. Which kind of brings us nicely to minimum spanning trees. And so you'll remember we briefly talked about this idea of a spanning tree when we were introducing graphs and just going through all the vocabulary. But just to remind you, a spanning tree is a structure, it's a tree, but what you do is you take your graph and essentially you want to use the minimum number of edges you can to connect all of the vertices in the graph. And so without making any cycles or anything within this structure. So you can see in this example, like the dotted lines make a spanning tree on this graph. So you don't need these solid lines, these edges, to be part of that. And remember that there can be many spanning trees for any given graph. It's not necessarily just one. So if we look at these, we can kind of assess this visually to say which of these is a spanning tree. So like, let's look at this first graph here. Is this a spanning tree represented?
No.
Why not?
Because of the cycle.
Right. So we've got a cycle here. So you know, by definition, you've got at least one extra edge that you don't need. What about this one here?
Also got an extra edge you don't need.
Right. I've also got a cycle, so kind of same thing. How about this here, considering this one graph? So it's a little bit trickier. Yes? So yeah, if you think about it, the keyword is spanning, right? So you've got to span all of the vertices in the graph. And so when you have a disjoint graph like this, that doesn't have, it needs another edge to be able to have a minimum spanning tree. And then how about everyone's favorite example, this lone vertex? Is it a minimum spanning tree?
Yes.
Yeah, it's always everything, isn't it? So.
Yeah, that one always messes me up.
It's always everything. Is it also the secret to life?
It may be, but there's always a note with it that says like only in the trivial case is it whatever, and so it's kind of pretty much useless. But
Oh, so it's trivial.
yeah.
But mighty conquests arise for trivial things.
So we can fix these. So this first one, if we wanted to do a minimum spanning tree, for example, take away an edge. You can take away any edge you want. Same thing with this one. As long as we take away an edge that forms the cycle, we now have a spanning tree. With the disconnected one, obviously, if we connect it somewhere, now we have a minimum spanning tree with these. Or not a minimum spanning tree, I'm sorry, a spanning tree. So for minimum spanning tree, we have to have weights on the edges. So that brings us to minimum spanning trees, which you will see affectionately called MST everywhere. So the idea here is that our graph will have weights on the edges, and we want to do the same thing that we did when we built a spanning tree, which is to go through all of the vertices without any cycles, but we also want to do it with the lowest weight path possible. So in this very, very simple example here, right, essentially you can see that to make a spanning tree, we just need to eliminate one of the edges. And so when we're considering a minimum spanning tree, we want to minimize the cost here, and so we will just remove the edge that has the highest weight in this case. And so that will make this a minimum spanning tree. If you think about this a little bit more, if you imagine that any two of these edges had equal weights, you could see that, and say that we had like this 0.4 is also 0.8. So then the choice is kind of arbitrary, right? It would be the same weight for either of the trees. So you can have multiple minimum spanning trees as well. Okay. So if we have a graph like this, where the weights are just listed on each edge, can we find the minimum spanning trees in this graph? And how many minimum spanning trees do you see in this graph? Anybody have an idea how many minimum spanning trees there may be? Two.
Yeah,
Two?
yeah.
Okay. Okay, so let's take a look at them. So one thing we could do, right, looking at it kind of up front, right, we know we have to go to all these vertices. So like C and D, right, those edges are going to have to be there no matter what. Where we do have some flexibility is in these edges. So all of these edges that are 4 here, we are able to still have a spanning tree and remove kind of any of these arbitrarily. And since 1 is low cost, we want to keep it. So we could remove between E and F, and we still have a minimum spanning tree. We could also remove between A and E, and we would have a minimum spanning tree. And of course, we could remove between B and F and still have a minimum spanning tree. And all of these are the same weight, and it's the minimum possible. So you can see, depending on the structure of the graph, you could have quite a few minimum spanning trees for the same graph. And so it's easy, like if you have a graph that you can actually see, that's not thousands of nodes, and you see something like these kind of redundant structures with similar weights, or the same weights, right? Then you can see like that's essentially like a branch there. It's a path then you could choose. But we typically will not have small graphs like this. And we want to do this obviously with code and have an algorithmic way of finding these minimum spanning trees. So that's the question we're going to look at today, is how can we find a minimum spanning tree in a weighted graph? And we'll look at two ways of doing that. So the first approach that we'll take is an algorithm called Prim's algorithm. And this is an approach that takes a weighted graph and it will produce a minimum spanning tree from that graph. So this is kind of considered a greedy algorithm. Have we heard that term before, greedy algorithms? So just to kind of characterize a greedy algorithm, a greedy algorithm tends to only think about the moment that it's in and make choices that are optimal based on that. So if you're kind of in like a big optimization process, a greedy approach will always, like whatever decision it's making in that moment, will do what's best for it there. It won't necessarily look back at the bigger picture and optimize with that in consideration. So greedy algorithms tend to be very fast, and they don't always produce an optimal result. So that's something to keep in mind when you see a greedy algorithm, is that usually it can produce an answer, but maybe not always the optimal result. In the case of Prim's algorithm, it does produce an optimal result, and we'll see why that's the case. So the complexity of Prim's algorithm, and we'll talk more about this on Monday, but depending on how you implement it, you can get these kind of very different complexities, and those are in terms of vertices and edges, as we always have with a graph. And we'll talk about the trade-offs of using Prim's versus a different algorithm, depending on your graph, right? Everything always kind of depends on the graph and its structure, and what's going to be the best. So let's look at what Prim's algorithm actually does. So the general approach is that you have a graph, and you just pick a random vertex to start at, right? So you go ahead and mark that vertex as being part of your minimum spanning tree. And then what you do is you look at all of the vertices that you have marked already as part of that tree, which in this case is just the first one. And you look at all of the edges that they have. And what you want to do is find the edge with the smallest weight that will connect you to a vertex that you don't have yet in your minimum spanning tree. And so that's the greedy step there, right? You're saying, I want to look at all of the possible edges, and I want to take the best one, and then add that to the set. Repeat this over and over until you have all of the vertices in your minimum spanning tree. So it's not a very complicated algorithm. It's kind of intuitive, and it does get the job done. So, kind of thinking about this, I've got a graph here. It's undirected, and I've got weights on all of the edges. The edges are these dotted lines. And so I've also got letters on each edge for convenience, and we'll use that with the next algorithm more. But so I've just got the letter and the weight that I've given it. And so I've got weights from 1 to, I think, 18 here. And they're paired with letters, and so like A is 1, B is 2, for simplicity. So for Prim's algorithm, I'll summarize here. We're going to start at a random vertex, and I'm going to choose vertex A to do that. So we'll start at A, and then what we're going to do is add it to our minimum spanning tree. And so I've just indicated that by putting these little dotted lines around A. It's part of the tree now. And so the first thing that we want to do is now look at all of the edges that are coming from the vertices that are part of our minimum spanning tree. So in our case, we just have A as our vertice as part of our tree. And so we have two choices here. We have edge D, which is a weight 4, and edge A, which is a weight of 1. So which of those edges would we choose? A, right? We make that greedy choice. We choose A because it is the lowest of the choices that we have in terms of weight. And so that adds this edge A to our tree, and more importantly adds E, this vertex, also to our minimum spanning tree. So now when we go to evaluate, we look at A's edges and we look at E's edges. and so we'll consider all of them. So in this case, when we look at the set of edges coming out of all of those that we haven't used yet, which one is now the lowest? C. Yeah. So you can see E has an edge C with weight 3. So we'll select that one. And that will add vertex C to our minimum spanning tree. And so now when we come back to consider that, we can now consider everything that we've got in A, E, and C in terms of our edges and look for the lowest. So if we do that, what do we find as our lowest?
D.
D, right? So D is weight 4. It's going from A to B, and that's not yet been connected, so we'll do that. Now we have added B to our list of vertices that are in our minimum spanning tree. So now when we look, what is the lowest weight edge that we find? So F is the lowest weight edge that we can use. The lowest weight edge is technically E here, right? It's 5. But it doesn't meet the criteria of linking something that's not already in the minimum spanning tree. So we do have to consider that as well, which is pretty easy to do, right? We keep a list of that. So yes, we will choose edge F, which is a weight of 6. And that will add the vertex F to our minimum spanning tree. So at this point, we take a look around. We see that we have a G7, but that's kind of the same case that we had with this E, right? That would add a link that's kind of redundant. So what do we see as the lowest now? Right, so down here we have H, which has a weight of 8, and that would connect us to D, which we don't have a connection to. So we'll go ahead and do that. And then you can kind of see that really opens up for us. We now have access to B, which has a weight of 2, and that would connect us to G, which we're not connected to. So we go ahead and take that. Okay, at this point, what looks like the lowest? Yeah, I think, does this look like, so I is 9, and it would connect us to H, which we're not connected to. Yeah. Okay, so we're getting close, right? We've kind of got most of these vertices visited, and we've only got I and J left. Okay, so where do we go now? Okay, so K's got a weight of 11, and that'll take us over to I. And then from there, we can see that our best choice, our only choice, is to go to J, 16. And so then this is the minimum spanning tree for this graph. So if you want to see, those were all the edges that we had, and these are the edges that actually minimize the cost of a spanning tree through the graph.
What was the steps of that again? You just pick a random one?
So what you do is you pick a random one to start. Yeah, you can start anywhere. And then from there, you start to pick the edges with the lowest weight that help you connect to something you're not connected to.
So why we go all the way from, like, we was over here at G.
Mm-hmm.
Why we go all the way to I?
All the way to I. So what we're doing is when we decide, like when we choose the next place that we're going, right, we look at all of the vertices we have and all of their edges and pick the lowest.
So you're not just picking the lowest or the latest one you're at, you're picking the lowest
one.
you're connected.
Yeah. So that can have, you can jump around a bit, right? You know, depending on how the weights are laid out.
So like I see like E5 is lower than I9, but we want to jump back down there. We gonna jump what's going on.
Right, because we've already connected, you know, like this would just add a cycle and it would be kind of useless to us. So yeah, we ignore that one. So yeah, that's the two things you're kind of balancing, right? You're ignoring things that would add a redundant connection or cycle, and you're picking the lowest thing that will connect you to something you're not connected to already. And so if you follow that procedure, you will get a minimum spanning tree for the graph. So thinking about why Prim's algorithm actually works, because we said it was greedy, right? And it's always doing that, like it's saying, okay, what's the lowest edge now where I'm at, not thinking about anything else. It's kind of intuitive why this works, right? So if you imagine that you start with no graph, right? And you're building the graph like a vertex or a node at a time, right? And so at every step of the way, it is always the minimum weight that it could be. You never add anything that puts like excess weight anywhere in the graph. And for that reason, the greedy approach works. So because you can think of it as building a graph, one vertex at a time, that's good. You can think of the graph you have as being a subgraph of the bigger graph, if you like. But that is what lets this greedy approach work for us. I guess I should mention, why would we want to find a minimum spanning tree?
To see which way to get to the end of the thing first, the fastest.
Yeah, so you think about any kind of application, right? Like whether these are airports or houses you're delivering something to, or a network that's moving data around. You'd like to know how to get from anywhere to anywhere. And you'd like to know kind of what that lowest cost way of doing that overall is. Now, there are much harder problems that you would like to solve within this, and we'll talk about those next week. But this is something that is helpful kind of on any application of a graph, is being able to traverse through from any vertex to any vertex on this overall low weight path. Okay, so let's talk about the second algorithm that we have that does this. This is called Kruskal's algorithm, and it is also a greedy algorithm, and it just takes a slightly different approach than we saw with Prim's. So if you noticed with Prim's algorithm, we were kind of always having to look at edges a lot and think about them, and this approach kind of just directly says, let's just look at edges and not focus on vertices so much. And we'll build our minimum spanning tree that way. And so we did a slightly different runtime here, which is a little bit nice and complicated. And we'll talk a little bit more next week about why it is exactly that. But know that these two algorithms are not, we can't say that one is categorically better than the other, even in worst case performance. It depends on the graph. Because you can see that the E and V are both terms in that runtime, right? And so if you have a bunch of vertices and very few edges, or a bunch of edges and very few vertices, that changes the balance of things, and which we've seen is the case for most things with graphs. So what we're going to do here is we're going to actually just look at these edges directly. And the reason that this greedy approach works is the same reason the other greedy approach works, is that we never add anything that we don't need, anything unnecessary. So what we're going to do is the first thing we'll do is we take a graph. We have all the weighted edges, and we're just going to sort them. We're going to sort them in order, 1, 2, 3, 4, like that. And then we are going to keep track of the vertices that we've added so far. And we're going to start with the smallest edge, and then go to the next smallest edge, the next smallest edge. And we will connect things if they need to be connected as we go. We'll repeat this until we have everything connected, which will be the number of vertices minus 1 for that number of edges. Okay, so we'll do it with the same graph that we had earlier. Kind of got a little summary form of this. So we will first kind of, conceptually remove all the edges. We're going to put them in a sorted list, which, if you think about it, could be a priority queue, which, if you think about it, could be a heap. Could be a min heap. So there you go, reusing those data structures, But we sort this out, okay? So, and then we put them in this queue. And now all we're going to do is, as long as there's something in the queue, we'll take the front of the queue, the smallest edge, out of it. And if the things that it's connected to are not already part of our minimum spanning tree, we will connect them. So, I'm going to start, in this case, with edge A, which has a value of 1. is connected to these two nodes here. And so we can obviously see at this point that connects to things that we aren't connected to. So we will go ahead and add those two and add that edge. Then we'll move immediately to the edge with the next lowest weight. So we're going to jump over here to B already, which has a weight of 2. And you can see it connects these two vertices that are not yet part of our minimum spanning tree. So what you might recognize already here is going on is we are actually building a number of disjoint graphs at the same time. And we will connect them once we find the edge that does that, that we need. So this does make the implementation a little bit interesting. We do have a way to do this that is efficient to check if these things are members of each other, because you've got to remember you are constantly having to check for everything what it's connected to and what it's not connected to for each of these steps. So it's one of those things that while we're looking at it visually and looking at the pseudocode version, it's really intuitive and easy. When you sit down to implement it, there are choices you can make that can make it efficient or inefficient. It's not necessarily a difficult thing to implement. It's just something you've got to give it a little bit of thought, make sure that you choose the right thing. And we'll talk about the implementation more next week as we talk about comparing the complexity and stuff like that. Okay, so we've added this edge, and now we're going to go to which edge?
C.
C, yes. So C has a 3 as its weight, so that's where we'll head next. And it connects us with a node that we were not connected to, a vertex that we were not connected to. And so that's good. We'll add that. Following kind of the same convention here with these dotted lines to say that we have added this vertex. So where do we go next?
F6.
We should have a 4 somewhere.
But it's connected.
Okay, so we have, D, which is 4, which would connect us to this node here, which we're not connected to. And so we do need that to make a minimum spanning tree. We've got to be connected to everything. So we can go ahead and add that. Now, our next edge, what is it?
F6.
Yes, okay, so F6, yes, that's the one we will add. So what about E5 here?
No, because it makes a cycle.
Right, makes a cycle, same thing as last time. So we'll just say goodbye to it and jump up here to F6. So we've done that. Next, we would look at 7, right? But that would not help us. That would be a cycle. So we'll go get rid of that. Yep. 8, that's a no on that. Or actually, sorry. 8, right?
We shouldn't have 8. Wait, should we have 8?
Yes, okay. So yeah, this is a step. Remember I said we've got these two disjoint graphs here? So we do, when we look at 8, we see that it would link these two nodes. And what we can also see is that what this node is linked to is its own disparate part, right? So this link is needed. And that's where I was telling you that the implementation has a little bit of a trick to it just to do this efficiently. Because you do have to know not only about these vertices, about their edges, but you need to know which component of the graph they're part of if they're separate from each other. And so in the implementation, you know that. And so when you check edge H here, which has the weight of 8, you can see that yes, it actually will connect these two components, and it does not form a cycle between anything. So we do add 8 in this case. Okay. So now we will look at 9. And I think we should add 9, right? Yeah. Okay, so we'll add 9. And then we know to look at 10, and that is, no. So that would be a cycle. 11. 11 look good? Yeah. 11 is good. Okay, then we will go to 12, which, no, 12 is just down there. 13, also a cycle, right? Okay, so now 14, no, that would also be a cycle. 15, same story there. And that brings us to 16, which is actually what we want. At this point, depending on the implementation, and I'm sure most implementations would detect that we're done. We don't need to actually look at the rest of these edges because we have covered each vertice, or if you want to just think in terms of edges, we have the number of vertices minus 1 edges. So we've met that condition. And we know, because of that, that we are finished finding that minimum spanning tree. And so there is our minimum spanning tree. It is the same minimum spanning tree that we got when we were using Prim's algorithm. And I'll be honest with you, I don't know on this example if there are other minimum spanning trees possible. I think there may not be. But you'd have to check, right? Yes?
Is this another way to do the algorithm?
Yeah. So these 2 ways to do the same thing. And depending on the graph, one can be better or worse. But in general, they're the same performance-wise. And there's just 2 different approaches to doing this. You'll find with like graph problems, it's the case a lot of times. There are, a bunch of different algorithms to do the same thing. And usually, like as time goes on, they get better. And so like we only learn the ones that do like a performance improvement. But with the early stuff, you kind of usually have a couple of different ways of doing things that are different, but may be roughly the same performance. So yeah, this will produce the minimum spanning tree for you, just like Prim's algorithm does. And it will have the same weight overall. So we'll talk about how we could find all of the minimum spanning trees next week, not just one minimum spanning tree, because right now, this is only going to give us 1, right? I should mention, so if we had an unweighted graph, we could do something that we've already learned if we wanted to find a minimum spanning tree. Any ideas what that would be? So if it's unweighted, you could kind of think of it as just the number of, edges being the weight. What? Yes, exactly. Breadth first search, yeah. Because if you remember, it always produces that shortest path for us. And so since everything, you can just assume the weight's equal, that kind of gives you the version for an unweighted graph. But these are very different problems. So these are kind of the 2 fundamental ways of doing a minimum spanning tree for the graph. We will get into doing actual shortest path on these weighted graphs. So this may be the lowest connection for your entire network. But if I want to go from one specific node to another specific node, there may be a bunch of different ways of doing that, and I want to find the lowest cost, which is a pretty common problem too. So next week we will get into that as well. Yeah, and I think that is all we have in terms of minimum spanning trees. So I will see everyone on Monday. Hope you have a good weekend.